What if I told you that you are a walking, talking star factory? That the very atoms building your body have traveled across galaxies and eons just to become you? This isn't science fiction. This is the universe's secret language, and we're about to become fluent. If you believe the world is more amazing than we can imagine, hit those like and subscribe buttons because we're diving headfirst into the code that writes reality itself, chemistry. Let's start with you. Take a look at your hand. Every single atom in your body, every bit of carbon in your cells, the calcium in your bones, the iron in your blood, with the single exception of hydrogen, was forged billions of years ago inside the heart of a star. When massive stars run out of fuel, they collapse and then explode in a supernova, an event so powerful it outshines entire galaxies. In that cosmic furnace, simple elements are crushed together to form heavier ones. These stellar guts, rich with the building blocks of life, are then scattered across the cosmos, eventually clumping together to form new stars, new planets, and eventually us. You are not just living in the universe, you are recycled stardust. You are a direct legacy of cosmic explosions. And that one exception, hydrogen? It's the universe's OG element. It is the simplest and most abundant substance in existence, making up roughly 75% of all normal matter by mass. Almost everything else is just a footnote. A hydrogen atom is beautifully simple. One proton and one electron. That's it. This simplicity is its power. It's the primary fuel for stars, including our own sun, which fuses about 600 million tons of hydrogen into helium every second. So while you're made of stardust, the star that makes your life possible is powered by the universe's most basic, fundamental building block. But this brings up an incredible cosmic detective story. We just mentioned helium, the byproduct of the sun's fusion. You'd think we found it on Earth first, right? Wrong. Helium was actually discovered on the sun nearly 30 years before it was ever identified on our own planet. In 1868, during a total solar eclipse, French astronomer Pierre Janssen was analyzing the sun's light through a prism. He noticed a bright yellow line in the spectrum that didn't match any known element. He realized he was looking at something entirely new. They named it helium, after Helios, the Greek god of the sun. It wasn't until 1895 that scientists found it trapped in uranium ore right here on Earth, confirming the cosmic discovery. We found an element 93 million miles away before we found it under our own feet. Thinking about new elements is always fun. If you had the chance to discover a new element tomorrow, what name would you give it? Let me know your most creative ideas in the comments. From the scale of the sun, let's shrink down to something you can hold. A single drop of water. It seems so small, so insignificant. Yet the chemistry packed inside is staggering. One tiny drop of water contains more H2O molecules than there are known stars in our entire Milky Way galaxy. Let that sink in. Scientists estimate there are between 100 to 400 billion stars in our galaxy. But a single drop of water? It holds over 1.5 sectillion molecules. That's a 1 with 21 zeros after it. The sheer number of atoms packed into the mundane world around us is so vast it's almost impossible to comprehend. Every sip of water you take contains more individual units than all the grains of sand on all the beaches on Earth many times over. This mind-bending property of water highlights how things aren't always what they seem, which is especially true for another common substance, glass. You've probably heard the myth that glass is actually a very, very slow-moving liquid, and that's why old church windows are thicker at the bottom. It's a romantic idea, but it's completely wrong. Glass is what chemists call an amorphous solid. In a normal solid, like a diamond or a salt crystal, the atoms are arranged in a neat, orderly, repeating lattice. They're locked in formation. But when you cool molten sand to make glass, it solidifies so quickly that its atoms don't have time to line up. They're frozen in a jumbled, chaotic, liquid-like arrangement. So it has the rigid structure of a solid, but the messy internal structure of a liquid. The reason old windows are thicker at the bottom is simply due to the imperfect glass manufacturing processes of the time. Chemistry doesn't just build our world, it creates our experiences. Think about the smell after a light spring rain. That fresh, earthy, clean scent has a name, petrichor. And that smell isn't just a byproduct of water hitting dirt, it's a specific chemical event. The star of the show is a compound called geosmin, which is produced by a type of bacteria in the soil called streptomyces. When raindrops hit dry ground, they trap tiny air bubbles. These bubbles then shoot upwards, bursting from the water and releasing a fine aerosol of particles, carrying the geosmin into the air. Our noses are incredibly sensitive to this compound. We can detect it at concentrations as low as a few parts per trillion. It's a primal scent, one that told our ancestors that life-giving rain had arrived, and it's all thanks to a molecule made by tiny microbes. From a scent in the air to a metal in your hand, chemistry is full of things that defy our expectations. And there's one element that does this better than almost any other. Imagine holding a solid, silvery piece of metal in your palm. It looks like something out of a sci-fi movie. You close your hand around it, and as your body heat transfers to it, the solid metal begins to melt. It turns into a shimmering, liquid puddle right in your hand, without burning you at all. This is gallium, with a melting point of just 76 degrees Celsius, or about 85 degrees Fahrenheit. It's one of the few metals that is liquid at near room temperature. It demonstrates a fundamental chemical property, the transition between states of matter, in the most direct and startling way possible. It's a solid that yields to the warmth of a human touch, a perfect example of the strange and wonderful rules that govern the elements. And it's just one of dozens of elements with properties so bizarre, you won't believe they're real. What if I told you the most magical spell you'll witness today isn't in a fantasy world, but in the steam rising from your coffee cup? That the universe is constantly performing incredible acts of alchemy right under your nose, turning the mundane into the magnificent. Chemistry isn't just a subject in a textbook, it's the secret language of your world. And once you start to understand it, you'll never see things the same way again. If you're ready to decode the everyday, make sure you hit that like button and subscribe for more mind-bending science. Let's start with a smell almost everyone loves, the scent of fresh rain after a dry spell. It has a name, petrichor, and it's not the water you're smelling. It's a complex chemical cocktail. For starters, plants secrete certain oils during dry periods, and when the rain comes, it displaces these oils, carrying them into the air. But the star of the show is a compound called geosmin, produced by a type of soil bacteria called actinomycetes. These bacteria ramp up their activity when the humidity rises just before a storm, and the force of the raindrops hitting the ground launches tiny aerosols containing geosmin into the air. Your nose is incredibly sensitive to this molecule. Humans can detect it at concentrations as low as 5 parts per trillion. That's like being able to smell a single drop of it in an Olympic-sized swimming pool. And to top it off, lightning during the storm can split oxygen and nitrogen molecules in the atmosphere, which then reform into nitric oxide and eventually ozone, adding a sharp, clean tang to the air. So that beautiful, earthy scent is a 3-part harmony of plant oils, bacterial byproducts, and supercharged air. From the smell of the storm to the sizzle in the kitchen, chemistry is the ultimate chef. Every time you sear a steak, toast a slice of bread, or roast coffee beans, you are initiating a cascade of reactions known as the Maillard reaction. This isn't just simple burning or caramelization, it's a specific chemical dance between amino acids, the building blocks of proteins, and reducing sugars. When heated to around 300 degrees Fahrenheit or 150 Celsius, they begin to react in a flurry, creating hundreds of new aroma and flavor compounds. The result is that delicious, savory, browned taste that's impossible to replicate by just boiling. This single reaction is responsible for the flavor profile of everything from fried onions and dark beer to chocolate and French fries. It's why a pale, steamed piece of chicken tastes so bland compared to its golden brown roasted counterpart. The complex, nutty, and roasted notes are all born from this beautiful chemical chaos, turning simple ingredients into a feast for the senses. Now, after that delicious meal, you have to do the dishes. And the hero of that chore, soap, performs a trick that's pure chemical genius. Greasy, oily messes won't just rinse away with water because, as we know, oil and water don't mix. This is where soap steps in. A soap molecule is what's called amphiphilic. It has two different personalities. One end, the head, is hydrophilic, meaning it loves water. The other end, the tail, is hydrophobic, meaning it fears water but absolutely loves oil and grease. When you lather up, these molecules get to work. The hydrophobic tails burrow into the grease on your plate, while the hydrophilic heads stick out facing the water. They surround the little droplets of grease, forming a sphere called a micelle, with the oil trapped safely inside and a water-loving shell on the outside. Now, the grease is effectively disguised as something water can grab onto. When you rinse, the water molecules grab the hydrophilic heads of the micelles and wash the whole package, soap, grease, and all, right down the drain. It's a brilliant act of chemical espionage happening in your kitchen sink. What's the one household cleaning product you absolutely can't live without? Let us know in the comments. I'm curious to see the chemical champions of your homes. From the kitchen sink to the desk drawer, another everyday object is hiding a chemical secret. We call them lead pencils, but they haven't contained any actual lead for centuries. The so-called lead is actually graphite, a stable form of the element carbon. Pure graphite is a soft, dark, metallic gray solid. But if you just stuck a rod of pure graphite in a pencil, it would be incredibly soft and messy. The magic lies in mixing it with a binder, clay. The exact ratio of graphite to clay is what determines the pencil's hardness. A pencil labeled 9H is very hard and contains more clay, leaving a light mark. It's perfect for technical drawings where precision is key. On the other end of the spectrum, a 6B pencil is very soft, contains much more graphite, and leaves a dark, smudgy line, favored by artists for shading. The familiar number 2 pencil, the standard for tests and daily writing, is a perfect middle ground, an engineered mixture of carbon and clay designed for the perfect balance of darkness and durability. Speaking of perfect balance, think about a piece of fruit. Its journey from hard and sour to soft and sweet is a carefully orchestrated chemical process managed by a single, simple molecule, ethylene gas. Ethylene is a plant hormone, and it acts as a ripening signal. As a fruit like a banana or tomato begins to mature, it starts producing this gas. The ethylene then triggers enzymes within the fruit to begin breaking down complex starches into simple sugars, making it sweeter. It also activates enzymes like pectinase, which breaks down pectin, the cellular glue that keeps the fruit firm, making it softer and juicier. This is why putting an unripe avocado in a paper bag with a banana speeds up the ripening process. The banana is a prolific ethylene producer, and the bag traps the gas, bathing the avocado in the ripening signal and telling it to get a move on. It's also the chemical reason for the old saying, "One bad apple spoils the bunch." A bruised or overripe apple releases a large amount of ethylene, which then signals all the healthy apples around it to start ripening and eventually rotting much faster. Now, let's look up, why is the sky blue? The answer isn't that the air is blue, but it has everything to do with the chemistry of our atmosphere and the physics of light. Sunlight appears white, but it's actually made up of all the colors of the rainbow. The Earth's atmosphere is about 78% nitrogen and 21% oxygen. These gas molecules are tiny, far smaller than the wavelength of visible light. When sunlight enters the atmosphere, it collides with these molecules. This causes the light to scatter in all directions, a phenomenon called Rayleigh scattering. However, and this is the crucial part, these tiny gas molecules are much more effective at scattering shorter wavelengths of light, like blue and violet, than they are at scattering longer wavelengths, like red and orange. So, as sunlight streams through the sky, the blue light is scattered all over the place, bouncing from molecule to molecule until it eventually reaches our eyes from every direction. The red and orange light, meanwhile, passes more or less straight through. This is why, when you look up at any point in the sky on a clear day, you see blue light that has been scattered by countless tiny molecules. From the sky above to the ground beneath our feet, chemistry is even giving our buildings superpowers. We think of concrete as a static, brittle material, but modern chemistry is turning it into a living, healing structure. Scientists have developed self-healing concrete by embedding it with tiny capsules containing a healing agent, typically a polymer or a mineral compound like sodium silicate, along with a catalyst. When a crack forms in the concrete due to stress or weathering, it ruptures these microscopic capsules. The healing agent is released and flows into the crack, where it makes contact with the catalyst. A chemical reaction is triggered, causing the agent to solidify and effectively glue the crack shut, restoring the concrete's structural integrity. Some versions even use dormant bacteria embedded in the concrete. When water enters a crack, it awakens the bacteria, which then produce calcite or limestone, biologically filling the void. This isn't science fiction. It's being used in projects today, promising a future with roads that mend their own potholes and buildings that heal their own wounds, all thanks to some cleverly applied autonomous chemistry. Imagine holding a solid block of metal in your hand. It's cool, it's heavy, and then it starts to melt, not from a blowtorch, but just from the warmth of your skin, pooling into a silvery liquid right in your palm. This isn't science fiction. This is the world of chemistry, and we're about to meet the rock stars, the recluses, and the downright dangerous characters that make up everything. Welcome to the Elemental Hall of Fame. If you're ready for a tour of the universe's most incredible building blocks, hit that like button and subscribe for more. Let's start with that melting metal. It's called gallium, element 31, and it's a true shapeshifter. Its melting point is just 29.76 degrees Celsius, or about 85 degrees Fahrenheit. This means on a hot summer day, a bar of pure gallium would turn into a puddle. Unlike mercury, it's non-toxic, so you can actually perform this magic trick yourself. But gallium has a more sinister-sounding party trick. It can weaken other metals through a process called liquid metal embrittlement. A drop of gallium on an aluminum can will make the ultra-strong aluminum so brittle you can tear it apart with your bare hands. It seeps into the boundaries between the aluminum crystals and just pries them apart. From a metal that's friendly to touch, we pivot to an element that would attack the very air you breathe. Meet fluorine. It's the most electronegative element, which is a fancy way of saying it is the most aggressive electron fief in the universe. It wants an extra electron so badly that it will rip it from almost anything. Fluorine can set fire to things we consider completely non-flammable. Water? Fluorine will react with it, producing flames. Glass? Fluorine will burn it. Asbestos, the famously fireproof material? You guessed it, fluorine will react violently with it. Chemists who first tried to isolate it faced explosions, toxic fumes, and equipment that was literally eaten away. They nicknamed it the tiger of the periodic table, and for very good reason. If fluorine is the hyper-aggressive tiger, then our next group of elements are the aloof, untouchable monks. For decades, the noble gases, helium, neon, argon, xenon, were called inert gases. The name itself meant they did nothing. They had a full outer shell of electrons and, according to all the chemical rules, had zero reason to react with anything. They were chemically perfect, complete, and boring. This was a fundamental truth of chemistry until 1962. A chemist named Neil Bartlett, working at the University of British Columbia, noticed that a platinum compound was reactive enough to steal an electron from an oxygen molecule. He then had a brilliant thought. The energy required to steal an electron from a xenon atom was almost identical. He decided to try the impossible. He mixed xenon gas with his platinum compound and, to the shock of the entire scientific world, created a new, stable, orange-yellow solid. It was the first ever noble gas compound. In that one experiment, a core law of chemistry was broken, and the inert gases suddenly weren't so inert after all. If you could name a newly discovered element, what would you call it? Let me know your most creative ideas in the comments. From the aloof to the almost non-existent, let's talk about rarity. You might think gold or platinum are the rarest things on Earth, but they aren't even close. That title likely goes to astatine, element 85. Astatine is so radioactive that it decays with incredible speed. Its most stable isotope has a half-life of just over 8 hours. This means that if you had a chunk of it, half of it would be gone by the end of your workday. Because it vanishes so quickly, it never has a chance to accumulate. Scientists estimate that at any given moment, the total amount of astatine present in the entire Earth's crust is less than a single gram. Not a kilogram, not an ounce. 1 gram spread across the whole planet. We know more about the surface of Pluto than we do about the basic chemistry of astatine, simply because it's impossible to gather enough of it to study before it disappears. Now, let's go from the rarest element on Earth to the most common element in the entire universe, hydrogen. It's element number 1 for a reason. Hydrogen makes up about 75% of all the mass in the cosmos. It's the fuel for stars, including our sun, through nuclear fusion. Every star you see is a giant ball of hydrogen getting crushed by its own gravity until it ignites. But here's the paradox. Despite being the most abundant thing out there, finding pure, elemental hydrogen gas here on Earth is incredibly difficult. It's so light that our planet's gravity isn't strong enough to hold on to it, so it just floats off into space. The vast majority of Earth's hydrogen is locked away in compounds, most famously by grabbing onto oxygen to form water. It's simultaneously everywhere and nowhere. What's the most surprising element fact you already knew? I'm curious to see what you've got. We've talked about the light and the rare, but what about the absolute edge of existence? Let's jump to the bottom of the periodic table, to the super heavy elements that don't exist in nature. The current heavyweight champion is adenosine, element 118. We have only ever synthesized a handful of individual atoms of this element by smashing smaller atoms together in a particle accelerator. And when we do make one, it exists for less than a millisecond before it tears itself apart through radioactive decay. We can't see it, we can't hold it, but we can predict its properties. And those predictions are wild. It sits with the noble gases, so it should be like them. But because its nucleus is so massive, with 118 protons, the immense positive charge makes its electrons orbit at speeds approaching the speed of light. This triggers strange relativistic effects. The result? Adenosine probably isn't a gas at all. It's predicted to be a solid at room temperature and possibly a semiconductor. We are creating new forms of matter that literally stretch the laws of physics as we know them. Now, let's bring it back to an element you interact with every single day, one hiding an explosive personality. I'm talking about sodium. For most of us, sodium means table salt, sodium chloride, but pure elemental sodium is something else entirely. It's not a crystal, it's a soft, silvery metal, so soft you can cut it with a butter knife, and it absolutely hates water. If you drop a small piece of pure sodium into water, it doesn't just dissolve, it skates across the surface, fizzing violently as it rips oxygen from the water molecules, releasing a huge amount of flammable hydrogen gas and immense heat. That heat is often enough to ignite the hydrogen, causing a dramatic and fiery explosion. It's a classic reminder that the elements on their own can be vastly different from the compounds they form. If you had to pick a favorite element, which one would it be and why? Drop your answer below. Finally, let's talk about an element of extremes, tungsten. You probably know it as the stuff inside old incandescent light bulbs. Why? Because tungsten has the highest melting point of any metal on the periodic table, at a blistering 3,422 degrees Celsius, or over 6,000 degrees Fahrenheit. It also has the highest tensile strength. But its name gives away another of its extreme properties. Tungsten comes from the Swedish words tungsten, which translates to heavy stone, and it is incredibly heavy. It's one of the densest elements in existence, packing as much mass into a small space as gold or uranium. A cube of tungsten the size of a milk carton would weigh over 150 pounds. This unique combination of density and heat resistance makes it critical for everything from military armor-piercing rounds to the vibrating motor in your cell phone. Is there a specific chemical reaction you find absolutely fascinating? Describe it in the comments. From metals that melt in your hand to gases that defy the rules, the periodic table isn't just a chart on a classroom wall. It's a cast of characters, each with its own incredible story. And we've only met a few of them. The tales get even stranger when these elements start to combine and react in the grand chemical theater that creates our world. Thanks for joining our tour of the Elemental Hall of Fame. If you enjoyed this journey, don't forget to hit like and subscribe so you don't miss our next chapter, where we dive into the explosive and transformative world of chemical reactions. What if I told you that the reason you can even exist, the reason a gecko can walk up a wall, and the reason a diamond is the hardest substance known, all comes down to a set of invisible rules of attraction and repulsion? We're about to pull back the curtain on the silent, powerful forces that build our world atom by atom. These are the chemical bonds and intermolecular forces, the unseen architects of everything. If you love seeing how the universe really works, do us a favor and tap that like button and subscribe for our full journey through the world of chemistry. Let's start with the ultimate atomic bully. In the world of elements, some are more desperate for electrons than others. This property, known as electronegativity, is essentially a measure of an atom's greed. And at the top of the periodic table, sitting on a throne of pure chemical desire, is fluorine. It is the most electronegative element in existence, period. It pulls on the shared electrons in a chemical bond with more force than any other atom. When fluorine forms a bond, it's less of a partnership and more of a hostile takeover. This extreme greed is why it's so reactive. It will rip electrons away from almost anything it touches, which is why compounds like hydrofluoric acid are so astonishingly corrosive, capable of dissolving glass. Fluorine's invisible, insatiable hunger for electrons creates a very visible and often violent impact on the world around it. From the strongest pull to a much gentler but arguably more important one, Let's talk about the humble water molecule, H2O. Oxygen is also quite electronegative, though not as much as fluorine. In water, it pulls the electrons from its two hydrogen partners closer to itself, creating a slight negative charge on the oxygen end and slight positive charges on the hydrogen ends. This makes water a polar molecule, like a tiny magnet. And when you have a glass full of these tiny magnets, they all start attracting each other. The positive hydrogen end of one molecule sticks to the negative oxygen end of another. This special attraction is called a hydrogen bond. It's not as strong as the bonds inside the molecule itself, but it's the invisible glue that gives water its superpowers. It's why water has such a ridiculously high boiling point for its size, why it can crawl up the inside of a plant stem, and crucially, it's why ice floats. As water freezes, these hydrogen bonds lock the molecules into a rigid, open lattice structure, making solid ice less dense than liquid water. If ice sank, lakes and oceans would freeze from the bottom up, wiping out almost all aquatic life. The gentle, invisible handshake of the hydrogen bond is literally the reason our planet can support life as we know it. But what if the force was even weaker? So weak it's almost not there at all, yet it can still allow creatures to defy gravity. Meet the van der Waals force. It's the weakest of all intermolecular forces, and it arises from a temporary, fleeting phenomenon. The electrons in an atom or molecule are constantly whizzing around. For a split second, there might be slightly more electrons on one side of an atom than the other, creating a temporary, lopsided charge, a tiny, instantaneous dipole. This flicker of charge can then influence a neighboring atom to do the same, causing a brief, weak attraction between them. It's like a faint, momentary whisper of a bond. On its own, it's almost nothing. But this is where the gecko comes in. The bottom of a gecko's foot is covered in millions of microscopic hairs called setae, and each of those hairs branches into hundreds of even tinier tips called spatula. This creates an enormous surface area. When a gecko places its foot on a wall, billions upon billions of these spatula get incredibly close to the surface. And all at once, these weak, flickering van der Waals forces between the gecko's foot and the wall add up to create an adhesive force so powerful it can support the gecko's entire body weight, even when hanging from a single toe on smooth glass. It's not suction, it's pure quantum chemistry. From the fleeting forces between molecules, we now turn to the powerful bonds that hold solids together. Let's look at metals. What makes a piece of copper so good at conducting electricity, or a piece of gold so easy to shape into jewelry? The answer is a unique type of chemical bond called a metallic bond. You can picture it like this. The metal atoms are arranged in a fixed, orderly lattice, but they've all agreed to give up their outermost electrons to a community pool. These electrons, now called delocalized electrons, are no longer tied to any single atom. Instead, they form a vast, mobile sea of electrons that flows freely throughout the entire metal structure, bathing the positive metal ions in a cloud of negative charge. This invisible sea is the secret to a metal's properties. It's why metals are such fantastic conductors of electricity and heat. The electrons are free to move and carry a current or transfer thermal energy. It's also why they are malleable and ductile. When you hit a metal with a hammer, the layers of atoms can slide past one another without breaking the bond, because the electron sea simply flows around them, holding everything together. Now, let's go from a community of sharing to an act of outright theft. This is the ionic bond, the classic story of a metal and a nonmetal. Take table salt, sodium chloride. Sodium, a metal, has one lonely electron in its outer shell that it would love to get rid of to become stable. Chlorine, a nonmetal, is just one electron short of having a full outer shell, which it desperately wants. When they meet, it's a perfect match made for larceny. The sodium atom willingly transfers its electron completely over to the chlorine atom. This isn't sharing, it's a permanent transaction. The sodium, having lost a negative electron, becomes a positive ion. The chlorine, having gained one, becomes a negative ion. And just like tiny magnets, these opposite charges attract each other with an immense electrostatic force, snapping together to form a bond. It's wild to think every grain of salt on your fries is a perfectly ordered city of ions. What other common substance has a surprisingly complex structure? Share your thoughts below. This powerful, invisible attraction is what arranges the ions into a rigid, highly ordered, and repeating three-dimensional structure called a crystal lattice, which is why salt forms those beautiful, brittle, cube-shaped crystals you can see with the naked eye. But what happens when atoms are more evenly matched and neither can steal electrons from the other? They share. This is the covalent bond, the foundation of most of the molecules that make up life, and it's responsible for one of the most dramatic contrasts in the material world: diamond versus graphite. Both are made of pure carbon and nothing else. The only difference is how their covalent bonds are arranged. In a diamond, each carbon atom forms 4 strong covalent bonds to 4 other carbon atoms, creating an incredibly rigid, interlocking tetrahedral lattice that extends in all 3 dimensions. This structure is what makes diamond the hardest natural substance known. To scratch a diamond, you have to physically break these powerful covalent bonds. Now look at graphite, the soft, flaky stuff in your pencil. Here, each carbon atom is bonded to only 3 others, forming flat, hexagonal sheets that look like chicken wire. The bonds within the sheets are very strong, but the bonds between the sheets are incredibly weak, just those gentle van der Waals forces we met earlier. This means the sheets can easily slide right off one another, which is exactly what happens when you write with a pencil. The same element, governed by the same invisible force of covalent bonding, can create both the ultimate abrasive and the perfect lubricant, all thanks to a simple change in geometry. This idea of molecular forces brings us full circle, back to the surface of water. We know hydrogen bonds hold water molecules together. But at the surface, where the water meets the air, something special happens. The water molecules at the surface have no other water molecules above them to bond with. As a result, they are pulled more strongly by the molecules beside and below them. This inward pull creates a kind of tension on the surface, causing the molecules to pack together more tightly, almost like an invisible, elastic skin. This is surface tension. It's strong enough to support the weight of a water strider, allowing it to skate across a pond. It's what pulls falling raindrops into perfect little spheres, the shape with the smallest possible surface area. And it's also the reason a belly flop hurts so much. When you hit the water flat, you aren't just hitting disorganized molecules. For a split second, you have to break through that incredibly strong, interconnected network of hydrogen bonds. You are momentarily fighting against one of the most powerful, invisible forces in chemistry, and the results are visibly and painfully obvious. These forces, from the tiniest flicker of attraction to the unbreakable grip of a diamond, are the silent engine of our physical reality. Imagine a liquid with a pulse, not a heartbeat, but a chemical one. You're looking at the Belousov-Zhabotinsky reaction, a mind-bending spectacle where a solution rhythmically changes color, cycling from clear to amber to deep blue and back again. For a long time, this was considered impossible. Chemists believed reactions should proceed in one direction, steadily moving toward a state of equilibrium, of bland uniformity. But this chemical clock defied that, creating oscillating patterns that spread like ripples in a pond. It was so counterintuitive that the scientist who first discovered it, Boris Belousov, had his paper rejected for years because it seemed to violate the fundamental laws of thermodynamics. It doesn't, of course, but it operates so far from equilibrium that it creates spontaneous, temporary order out of chaos, a true rule breaker in the world of beakers and flasks. From a reaction that pulses with light to one that simply is light. Think about a firefly on a summer night or the snap of a glow stick. You're witnessing chemiluminescence, one of the most efficient energy transformations known to science. When you burn a log, most of the energy is wasted as heat, with only a tiny fraction escaping as light. But in the chemical reaction inside a glow stick, there's almost no heat produced at all. The reaction is so finely tuned that it converts chemical energy directly into photons with staggering efficiency, sometimes over 99.9%. It's cold light, a reaction that rewrites the rule that says fire must be hot. Instead of wasting energy warming up its surroundings, it pours nearly all its power into the simple, beautiful act of glowing in the dark. But not all reactions are so gentle. Some are designed for pure, unadulterated destruction. Meet Fenton's reaction, the chemical equivalent of a black hole for unwanted organic molecules. By combining simple hydrogen peroxide with a bit of iron, you unleash a chemical monster. The reaction produces hydroxyl radicals, which are among the most reactive and powerful oxidizing agents in existence. They are so voraciously destructive, they will rip electrons from almost any organic compound they encounter, tearing it apart molecule by molecule. This process is used in advanced water treatment to annihilate stubborn pollutants like pesticides and industrial dyes, effectively erasing them from existence. It's chemistry's ultimate cleaner, a reaction that doesn't just cover up a mess, but obliterates it at the atomic level. It makes you wonder, what's the most difficult thing you've ever had to clean up? Let us know in the comments below. From total destruction, let's turn to creation. Specifically, the creation of flavor. The next time you bite into the crust of perfectly baked bread, seared a steak, or smell the rich aroma of roasted coffee, you are experiencing the Maillard reaction. This isn't a single reaction, but a sprawling, chaotic city of chemical changes that occurs when sugars and amino acids are heated. It's what creates that beautiful brown color and hundreds of new, complex flavor and aroma compounds that weren't there to begin with. It's not just burning, it's a delicate dance that rewrites the very essence of food. The same piece of raw dough is bland and uninteresting, but after the Maillard reaction, it's a symphony of taste. It's the reason why a boiled potato tastes so different from a golden brown French fry, proving that sometimes the most delicious rules are the ones written by heat and chemistry. The Maillard reaction is a slow, delicious burn. But what if you need a reaction that is the exact opposite, instantaneous and utterly reliable? For that, rocket scientists turned to hypergolic propellants. These are pairs of liquids, a fuel and an oxidizer, that have a rather dramatic relationship. The moment they touch, they ignite. Instantly. There's no need for a spark plug, a flame, or any kind of ignition system. The very chemistry of their meeting is so violent and exothermic that they can't help but explode into a controlled, propulsive fire. This makes them incredibly reliable for spacecraft engines that need to fire in the vacuum of space, sometimes years after launch. It's a reaction that rewrites the need for a trigger, where the simple act of contact is the only catalyst for furious, powerful combustion. This idea of triggering reactions in unusual ways gets even stranger. We've seen reactions started by heat and by simple contact, but what about sound? Welcome to the bizarre field of sonochemistry, where chemical reactions are driven by ultrasonic sound waves. When high-frequency sound is blasted through a liquid, it creates and collapses microscopic bubbles in a process called acoustic cavitation. For a fleeting moment, the inside of each collapsing bubble becomes an extreme environment, reaching pressures of over 1,000 atmospheres and temperatures hotter than the surface of the sun, around 5,000 degrees Celsius. These tiny, intensely hot bubbles act as microreactors, forcing molecules together and dramatically accelerating reaction rates, sometimes by a factor of 1,000,000. It's a technique that rewrites the very tools of the chemist, replacing the Bunsen burner with the speaker. We've seen reactions that pulse, glow, destroy, create, and ignite on contact. But some reactions don't just rewrite the rules of a single experiment, they rewrite the rules for all of humanity. In the early 20th century, scientists faced a crisis. The world was running out of fertilizer, and with it, the ability to grow enough food. The problem was nitrogen. Our air is nearly 80% nitrogen, but it's in a form, N2, that is incredibly stable and useless to plants. The two nitrogen atoms are bound by a powerful triple bond. Fritz Haber and Carl Bosch developed a process to do the impossible. Under immense pressure and high temperatures, using a catalyst, they could crack that triple bond and combine atmospheric nitrogen with hydrogen to create ammonia. This ammonia is the foundation of modern synthetic fertilizers. The Haber-Bosch process literally pulls food out of thin air. It is estimated that this single chemical reaction is responsible for sustaining the lives of half the people on Earth today. Without it, our global population would be less than half of what it is. It's not just a reaction that rewrote the rules of chemistry, it's the reaction that rewrote the future of our species. Forget factories and power grids for a moment. The most complex, efficient, and mind-boggling chemical plant on the planet is you. Right now, trillions of coordinated reactions are happening inside your body, a symphony of molecular precision that makes our grandest engineering feats look like child's play. We've explored the elements and their explosive tendencies, but now we dive inward into the very chemistry that allows a thought to form or a heart to beat. We're talking about the chemical foundation of life itself. It all begins with a substance so common we barely think of it as a chemical: water. But H2O is perhaps the weirdest molecule in the universe, and its strangeness is the reason you exist. Unlike molecules of similar size, which are gases at room temperature, water is a liquid because of its shape. The two hydrogen atoms aren't in a straight line with the oxygen. They form a V, or a bent shape. This creates a slight positive charge on the hydrogen side and a slight negative charge on the oxygen side, making it a polar molecule. This polarity is a superpower. It turns water into the universal solvent, allowing it to pry apart salts and dissolve vital nutrients, transporting them through your bloodstream. These same polar bonds, called hydrogen bonds, are why water has such a high specific heat, meaning it can absorb a lot of energy before it gets hot. This is your body's built-in air conditioning, preventing you from overheating every time you go for a jog. Every single life-sustaining reaction in your cells happens in this weird, wonderful chemical soup. But a soup needs ingredients, and for life on Earth, the master ingredient is carbon. What makes carbon so special? It's social life. Carbon has 4 valence electrons, meaning it's constantly looking to form 4 stable covalent bonds. This makes it the ultimate Lego brick of biochemistry. It can bond with itself to form long, stable chains, branched trees, and even complex rings, creating a vast architectural skeleton for other atoms to attach to. It can form single, double, or even triple bonds, each with different shapes and properties. This versatility is why we have such a staggering diversity of organic molecules, from the simple sugars that give you energy, to the complex lipids that form your cell membranes, and the proteins that do, well, almost everything. Every piece of you that isn't water is built around a framework of carbon atoms, a testament to its unmatched ability to build large, complex, and stable structures. But here's where it gets truly bizarre. It's not just that carbon builds these structures, it's that life has a very specific preference for how they're built in 3D space. Many organic molecules are chiral, meaning they exist in two forms that are mirror images of each other, like your left and right hands. They are chemically identical, but not superimposable. In the lab, making these molecules usually produces a 50-50 mix of both left-handed and right-handed versions. But in your body, life almost exclusively uses left-handed amino acids to build proteins and right-handed sugars like glucose for energy and structure. Why? Nobody knows for sure. It's one of the deepest unsolved mysteries in biology. This property, called homochirality, is a universal signature of life on Earth. If we ever find life elsewhere, checking the handedness of its molecules could be a key test. If you could have any superpower, what would it be? For me, it would be to travel back in time and see what event made life choose one mirror image over the other. What's your best wild theory for this cosmic coin flip? Let me know in the comments below. This incredibly specific chiral machinery of life requires a constant supply of energy to run. It can't just plug into a wall socket. Instead, every living cell uses a universal rechargeable battery in the form of a molecule called adenosine triphosphate, or ATP. Think of it as the energy currency of the cell. When your body breaks down food, it uses that chemical energy to stick a third phosphate group onto a molecule of adenosine diphosphate, or ADP, creating the high-energy ATP. This molecule then travels to wherever energy is needed: a muscle cell contracting, a neuron firing, a protein being built. When the energy is required, that third phosphate bond is broken, releasing a burst of power, and the molecule reverts back to ADP, ready to be recharged. Your body is in a constant state of recycling ATP. On an average day, you will generate and break down a weight of ATP nearly equal to your own body weight. It's an endless, lightning-fast cycle of charging and spending that powers every moment of your existence. And the instructions for building all this machinery, for managing this energy, for dictating every aspect of what you are, is stored in another famous molecule, deoxyribonucleic acid, or DNA. We all know its iconic double helix shape, but the sheer chemical efficiency of its data storage is staggering. Your DNA uses a four-letter alphabet, the nucleotide bases adenine, guanine, cytosine, and thymine, to write the most complex instruction manual ever created. The density of this information storage is beyond anything humans have engineered. A single gram of DNA can theoretically store around 215 petabytes of data. To put that in perspective, that's 215 million gigabytes. All the movies ever made, all the books ever written, all the music ever recorded could be stored in a clump of DNA that would fit in the palm of your hand. It's achieved through an elegant system of hydrogen bonds holding the two strands of the helix together, with the A's always pairing with T's and C's always pairing with G's, ensuring a perfect, stable copy can be made every time a cell divides. Having this perfect blueprint is one thing, but you need workers who can read it and act on it. In the cell, this is where enzymes come in. Enzymes are biological catalysts, almost always proteins, that speed up chemical reactions without being consumed in the process. And when we say speed up, we don't mean by a little bit, we mean by factors of millions, billions, or even trillions. For instance, a simple reaction like adding water to carbon dioxide might happen on its own a few times an hour. But in your red blood cells, an enzyme called carbonic anhydrase makes that same reaction happen up to 1,000,000 times per second. It does this through its unique 3D shape, which creates a perfectly formed active site that a specific molecule or substrate can fit into like a key into a lock. This brings the reactants together in the perfect orientation, lowering the energy needed for them to connect. Without enzymes, the reactions needed to digest your food, contract your muscles, or even think would be so slow that life as we know it would be completely impossible. And perhaps the most magnificent enzymatic process of all is the one that powers nearly all life on the planet: photosynthesis. On the surface, the equation looks simple. Carbon dioxide plus water, with a little sunlight, becomes glucose and oxygen. But the chemistry behind it is a masterpiece of quantum mechanics. It all hinges on the pigment molecule chlorophyll, which has a unique structure that allows it to become excited by very specific wavelengths of light, primarily red and blue. When a photon of light strikes a chlorophyll molecule, it knocks an electron into a higher energy state. This high-energy electron is then passed down a sophisticated chain of other molecules, an electron transport chain, in a process that generates those ATP batteries we talked about earlier. This intricate dance of photons and electrons ultimately provides the energy to rip apart water molecules, one of the most stable compounds there is, and use their parts to build sugar molecules from carbon dioxide. It's life's way of turning pure light into solid matter, the ultimate chemical magic trick that forms the base of almost every food chain on Earth. Imagine a solid material that's almost entirely made of empty space, a substance so light it can be balanced on the petals of a flower. Or picture a liquid with a smell so horrifically potent that a single dropped vial once forced the evacuation of an entire city. We've covered the elements and their everyday partnerships, but now we venture into the wild side of chemistry. We're exploring the molecules that defy expectation, the compounds that exist on the very edge of stability, and the materials that seem to be pulled from the pages of science fiction. We begin with a metal that seems to have a flair for the dramatic: gallium. At first glance, it looks like any other silvery metal, solid and unassuming. But hold a piece in your hand, and a strange transformation begins. Gallium possesses an unusually low melting point of just under 30 degrees Celsius, or about 86 Fahrenheit. This means the warmth of your own body is enough to turn this solid metal into a shimmering, liquid puddle in your palm. But its party trick doesn't stop there. Gallium is a chemical bully to other metals, particularly aluminum. If you scratch an aluminum surface and apply a drop of liquid gallium, it will begin a process called liquid metal embrittlement. The gallium atoms seep into the aluminum's metallic structure, disrupting the bonds that hold it together and making the once strong metal incredibly brittle, capable of being torn apart with your bare hands. This isn't just a curiosity. Gallium arsenide is a crucial semiconductor used in high-frequency electronics, proving that even the most eccentric elements have a practical side. From a metal that melts in your hand, we move to a liquid that dances at your command. Meet ferrofluid. It looks like a pool of black ink, but it's hiding a secret. This liquid is packed with billions of nanoscale magnetic particles, each coated with a surfactant to prevent them from clumping together. In its normal state, it behaves like any other liquid. But bring a magnet close, and the ferrofluid comes alive. It erupts into a mesmerizing crown of sharp, intricate spikes that trace the invisible lines of the magnetic field. It's a liquid porcupine, an alien landscape forming and reforming in real time. The closer the magnet, the higher and sharper the spikes become. This isn't just for show. Ferrofluids are used in high-end speakers to dampen vibrations for clearer sound, in hard drives to form liquid seals, and are even being explored for targeted drug delivery within the human body. It's a beautiful, hypnotic demonstration of physics and chemistry working in perfect, spiky harmony. Now, let's talk about that solid made of nothing. It's called aerogel, and it holds the record for the world's least dense solid material. Nicknamed solid smoke or frozen smoke, it's created by taking the liquid out of a gel and replacing it with gas, leaving behind only the delicate solid silica framework. The result is a substance that is up to 99.8% air. A block of it the size of a person would weigh less than a pound. But don't let its ethereal appearance fool you. Aerogel is remarkably strong for its weight. A small piece can support thousands of times its own mass. Its true superpower, however, is its incredible ability as an insulator. The vast network of tiny, air-filled pores traps heat transfer with astonishing efficiency. You can hold a blowtorch to one side of a thin sheet of aerogel while a delicate flower sits unharmed on the other. This property has made it invaluable to NASA, which has used it to insulate electronics on Mars rovers and to capture super-fast comet dust in space without destroying the particles upon impact. From a material that's barely there, we pivot to a compound whose presence is impossible to ignore. We need to talk about thioacetone. This organosulfur compound has earned the undisputed title of the worst-smelling chemical known to science. It's not just bad, it's legendarily, powerfully, and aggressively foul. The stench is an overwhelming, room-clearing combination of garlic and decay, but amplified to an unbearable degree. In 1889, chemists in the German city of Freiburg attempted to produce it, resulting in an accidental release. The effect was immediate and catastrophic, causing spontaneous nausea and vomiting throughout the area and forcing a complete evacuation of the surrounding city blocks. Its potency is hard to comprehend. Chemists report that a single drop escaping a container in a sealed fume hood can be detected by people in buildings hundreds of meters away within seconds. The experience is so profoundly unpleasant that most labs have abandoned any work with it entirely. Speaking of unforgettable lab experiences, what's the most powerful smell you've ever encountered, good or bad? Drop your story in the comments below. Let's see what can compete with thioacetone. If thioacetone is chemistry's greatest offense to the nose, then our next subject is its most violent actor, cesium. Sitting at the bottom of the alkali metals, cesium is the most reactive and most electropositive of all stable elements. Its atoms are large, and its single outermost electron is held so loosely that it's practically desperate to give it away to bond with something, anything. This eagerness leads to explosive consequences. When exposed to air, it ignites instantly. But its most famous reaction is with water. Drop a piece of cesium into water, and the result is not a gentle fizz, but a massive, instantaneous explosion. It rips hydrogen atoms from the water molecules so violently that the heat generated immediately ignites the hydrogen gas, creating a powerful shockwave. This extreme reactivity is why you'll never find pure cesium in nature. Yet, this volatile element has a surprisingly precise and gentle side. It's the heart of the world's most accurate atomic clocks, which define the international standard for what a second is. But even the explosive power of cesium pales in comparison to a compound so unstable it borders on the absurd. Its name is azeto-azide azide, with the chemical formula C2N14. Containing an astonishing 14 nitrogen atoms bound together in a high-energy, unstable arrangement, it is arguably the most sensitive explosive compound ever created. Nitrogen atoms are happiest when they are triple bonded to each other as N2 gas, a very stable and low-energy state. This compound forces them into a chain of weak single and double bonds, creating a molecule that is bursting with pent-up energy. It is so ridiculously sensitive that almost any external stimulus can cause it to violently decompose back into nitrogen gas. Attempting to touch it, move it too quickly, expose it to bright light, or even just dissolve it in a solution has been reported to cause it to detonate. Chemists who have worked with it say it's less a compound and more a catastrophe waiting to happen, existing on a knife's edge between being and not being. Finally, we journey from the explosively real to the theoretically terrifying. Meet octaazakibane. This molecule, with the formula N8, does not yet exist, but it haunts the dreams of theoretical chemists. It's a hypothetical allotrope of nitrogen, where 8 nitrogen atoms are arranged at the corners of a perfect cube. Just like in azide, this structure forces the nitrogen atoms into strained, high-energy single bonds they despise.
The energy locked within this molecular cage would be immense. If it could ever be synthesized, it would be an explosive with an energy density many times greater than TNT. But its most compelling feature is that upon detonation, its only byproduct would be harmless nitrogen gas, making it a green explosive of unimaginable power.
For now, it remains a tantalizing what if, a perfect cube of pure energy that reminds us that even after centuries of discovery, chemistry's most exotic frontiers may still be waiting for us just beyond the horizon. What if I told you that everything you see, everything you touch, the device you're watching this on, even your own body, is a ghost? A magnificent illusion built from almost nothing at all. Today, we're not just looking at chemistry. We're peeling back the fabric of reality itself to uncover the bizarre rules that make matter, well, matter. And if you love having your mind blown by the secrets of the universe, make sure to hit that subscribe button and ring the bell so you don't miss a thing. Let's start with that ghost in the room. You feel solid, right? But the atoms that make you up are staggeringly, incomprehensibly empty. The nucleus at the center is unbelievably tiny compared to the space the electrons occupy in their orbital clouds. We're talking 99.99999999996% empty space. To put that into perspective, if you could magically remove all the empty space from the atoms of every single human being on Earth, all 8 billion of us, the entire human race would be compressed into a volume no bigger than a single sugar cube. Everything that makes us who we are, every thought, every memory, every person, condensed into something you could lose in your pocket. The solidity we experience is just an illusion created by electrons repelling each other. We are, in a very real sense, phantoms held together by invisible forces. But if we're mostly empty space, things get even weirder when particles decide to move through it. You'd think a solid wall is a pretty good barrier, but on the quantum level, it's more like a suggestion. There's a phenomenon called quantum tunneling, where a subatomic particle can pass directly through a barrier it shouldn't have enough energy to overcome. It's like throwing a tennis ball at a brick wall and having it just appear on the other side. This isn't science fiction, it's the reason our sun shines. The immense pressure at the sun's core isn't quite enough to force hydrogen nuclei to fuse on its own. But thanks to quantum tunneling, they can cheat, phasing through each other's repulsive barriers to merge and release the energy that powers our solar system. The light and heat you feel from the sun are a direct result of this ghostly quantum trick. So particles can phase through walls, but what stops everything from just collapsing into a single dense point? If atoms are mostly empty space and particles can tunnel, why do we have structure at all? The answer lies in one of the most fundamental rules of the universe, a piece of cosmic code called the Pauli exclusion principle. It states that no two identical fermions, particles like electrons, can occupy the same quantum state simultaneously in the same atom. Think of it as the universe's strictest bouncer. Each electron needs its own unique ID, defined by 4 quantum numbers. If one electron has a certain set of these numbers, no other electron in that atom is allowed to have the exact same set. This principle forces electrons into higher and higher energy shells, creating the diverse atomic structures that give us the entire periodic table.
Without it, all electrons would pile into the lowest energy level, and chemistry as we know it would cease to exist. There would be no elements, no molecules, no us. The very substance of the universe is built on this rule of exclusion. If you could break the Pauli exclusion principle for just 1 second, what do you think would happen to the world? Drop your most creative or chaotic ideas below. This rule governs the electrons, but what about the protons and neutrons they're orbiting? For a long time, we thought they were fundamental, but we were wrong. They're made of even smaller, more exotic particles called quarks. And here's where it gets colorful. Quarks come in 6 different types, or flavors: up, down, charm, strange, top, and bottom. A proton, for instance, is made of 2 up quarks and 1 down quark. But that's not all. Each quark also possesses a property called color charge, which comes in red, green, or blue. These aren't actual colors you can see, but a way to describe the charge of the strong nuclear force, the most powerful force in the universe, which glues these quarks together. For a particle like a proton to be stable, its quark colors must combine to be white or colorless, like mixing red, green, and blue light. So the very core of your atoms is a swirling dance of flavors and colors, a subatomic symphony holding you together. But for every particle in that symphony, the universe has a dark twin. Every quark, every electron has a corresponding antiparticle. An antiproton has a negative charge. A positron is an anti-electron with a positive charge. They are identical in mass, but opposite in every other way. And when matter meets its antimatter counterpart, they don't just collide, they annihilate. They vanish in a flash of pure energy, in perfect accordance with Einstein's famous equation, E equals mc squared. The energy release is colossal. The annihilation of just 1 gram of antimatter with 1 gram of matter would unleash more energy than the atomic bomb dropped on Hiroshima. This raises one of the biggest questions in physics. If matter and antimatter were created in equal amounts during the Big Bang, why is our universe made almost entirely of matter? Where did all the antimatter go? What scientific mystery fascinates you the most? Is it dark matter, the origin of life, or something else entirely? Let me know in the comments. This dance of opposites isn't just about matter and antimatter. It exists on the molecular level in a much more subtle and sometimes tragic way. Many molecules in our bodies are chiral, a property named after the Greek word for hand. Just like your left and right hands are mirror images of each other but can't be perfectly superimposed, these molecules exist in 2 mirror image forms. They have the exact same chemical formula, but their 3D arrangement is different. This handedness is critical. Your body might only be able to use the left-handed version of an amino acid or a right-handed version of a sugar. The most devastating example of this was the drug thalidomide in the 1950s. The right-handed molecule was a safe and effective sedative for pregnant women. But its left-handed mirror image, which was also present in the medication, was a teratogen that caused horrific birth defects. It's a stark reminder that in chemistry, shape is everything. Can you think of any other everyday examples of handedness or chirality in nature? Share what you find. The secrets of matter go even deeper, connecting chemistry to the most mind-bending theories of physics. Take the element gold. Have you ever wondered why it has that beautiful, distinctive yellow color, while most other metals like silver, platinum, and aluminum are just silvery white? The answer is Einstein's theory of relativity. Gold is a heavy element with 79 protons in its nucleus. This massive positive charge pulls its inner electrons into orbit at incredible speeds, more than half the speed of light. According to special relativity, as an object approaches the speed of light, its mass increases and lengths contract.
For gold's electrons, this relativistic effect makes them heavier and pulls their orbits closer to the nucleus. This shift in electron orbitals changes the wavelengths of light the atom absorbs. Gold absorbs blue light more strongly, reflecting yellow and red light back to our eyes. Without relativity, gold's electrons would behave differently, and it would absorb light in the ultraviolet range, making it look silvery, just like its neighbors on the periodic table. The color of gold is literal, physical proof of Einstein's theory in action, a cosmic speed limit written into the very fabric of an element. If you could change the color of one element just by tweaking its electrons, which would it be and what color would you choose? Get creative. From the vast emptiness of an atom to the relativistic secret behind a piece of jewelry, the mysteries of matter are everywhere. We've seen that the universe is emptier, stranger, and more connected than we could ever imagine. But what happens when we push this matter to its absolute limits of temperature and pressure? The rules change, and the very states of existence begin to blur. That's where we're headed next. There's a liquid so violent it will force molecules that have no business accepting a proton to take one anyway. A liquid so powerful it makes pure sulfuric acid look like drinking water. And it's just the tip of the iceberg in the utterly astonishing world of acids and bases. Forget the simple red and blue paper of high school labs. The reality is a story of stolen protons, ravenous electron pairs, and chemical definitions that had to be rewritten over and over again. We often take these terms for granted, but our very understanding of them is built on centuries of discovery and debate. The journey begins with something incredibly simple: taste. The word acid itself comes from the Latin word acetus, which simply means sour. Early chemists, in a practice we absolutely do not recommend, identified acids by their characteristic sharp, sour taste. Think of the citric acid in lemons or the acetic acid in vinegar. This sensory-based classification was the first step, grouping substances by a shared, observable property. For a long time, this was the most advanced method they had. But it led to a massive and fundamentally incorrect assumption about what made an acid an acid. The brilliant French chemist Antoine Lavoisier, often called the father of modern chemistry, was convinced he had cracked the code. He observed that when many non-metal elements were burned, they formed substances that, when dissolved in water, created acids. The common denominator? Oxygen. So he proposed that oxygen was the essential acid-forming element. He was so certain that he embedded this idea into the very name he coined for the element, oxygen, derived from Greek roots meaning acid former. This powerful idea dominated chemical thought for decades. It took the daring experiments of Sir Humphrey Davy to topple this pillar. By studying a substance then known as muriatic acid, he conclusively proved it contained hydrogen and chlorine, but no oxygen. He demonstrated that it was hydrogen, not oxygen, that was the true common thread among acids. That substance is now known as hydrochloric acid, the very acid in your stomach. With hydrogen identified as the key player, the stage was set for the first truly scientific definition. Swedish chemist Svante Arrhenius proposed that acids were substances that increased the concentration of hydrogen ions, basically just protons, when dissolved in water. Bases, in turn, were substances that increased the concentration of hydroxide ions. This was a revolutionary leap forward, finally moving chemistry beyond simple observation and into the realm of molecular behavior. It explained so much, and for this breakthrough, Arrhenius was awarded the Nobel Prize. But his elegant theory had a fatal flaw. It was completely dependent on water. It couldn't explain why a substance like ammonia acted as a base in other solvents or even in the gas phase. Chemistry needed a bigger, more universal idea. And it got one, thanks to two chemists working independently, Johannes Brønsted and Thomas Lowry. They shifted the entire paradigm. Instead of focusing on what acids and bases produce in water, they focused on what they fundamentally do in any reaction. They defined an acid as a proton donor and a base as a proton acceptor. Simple, brilliant, and incredibly powerful. This new definition beautifully explained the mystery of ammonia. Ammonia has no hydroxide ions to donate, but its nitrogen atom has a lone pair of electrons that desperately wants to grab a proton from another molecule, like water, making it a classic proton acceptor, a Bronsted-Lowry base. This donor-acceptor relationship became the new gold standard for understanding a vast range of chemical reactions, freeing the concept from its watery cage. But chemistry's quest for the ultimate definition wasn't over. The legendary American chemist Gilbert N. Lewis, famous for his work on chemical bonding, proposed the most sweeping and inclusive definition of them all. He zoomed out even further, from the proton to the electrons that form the bonds themselves. In his view, the real action wasn't the transfer of a proton, but the sharing of an electron pair. A Lewis acid, therefore, is any substance that can accept a pair of electrons, and a Lewis base is any substance that can donate a pair of electrons. This definition is so broad and powerful that it includes a whole new universe of substances as acids, things that have no hydrogen at all. A compound like boron trifluoride can act as a potent Lewis acid because its central boron atom is electron deficient and eager to accept an electron pair from a donor. What's the most obscure or fascinating acid or base you remember learning about? Share it in the comments below. This journey through definitions leads us to the absolute extremes of chemical reactivity, the superacids. These are substances so acidic, they defy the traditional pH scale. The undisputed champion is fluoroantimonic acid. To call it strong is a colossal understatement. It is an astonishing 10 quadrillion times more acidic than 100% concentrated sulfuric acid. That's a 1 with 16 zeros after it. It's so powerful it will protonate, or forcibly jam a proton onto, nearly any organic compound, including substances like methane, which are famously unreactive. It rips molecules apart, creating hyperreactive ions called carbocations that chemists can then study. Handling it is a nightmare. It will react with and dissolve glass, so it must be stored in special Teflon-coated containers. You don't need to look to exotic labs to find astonishingly powerful acids, though. You're carrying one around with you right now. Your stomach produces hydrochloric acid to digest food and kill pathogens. At its peak concentration, this stomach acid can reach a pH of 1.5. That is intensely acidic, fully capable of dissolving a piece of zinc metal. So, why doesn't this potent chemical dissolve your own stomach? The answer is a biological marvel, a thick, robust layer of mucus secreted by specialized cells in the stomach lining. This mucus is rich in bicarbonate ions, a base, which instantly neutralizes the acid right at the surface, creating a protective barrier that keeps the corrosive liquid safely contained. It's a perfect, self-regulating chemical defense system. Are there any other incredible feats of biochemistry that just blow your mind? I'd love to read about them in the comments. For centuries, before we had digital pH meters, chemists needed a quick way to tell acids and bases apart. Their go-to tool became the famous litmus test. That simple strip of paper, turning red in acid and blue in base, is a staple of every introductory chemistry class. But it's not some high-tech synthetic indicator. Litmus is a natural dye mixture extracted from lichens, primarily the species Roxella tinctoria. For hundreds of years, this fungus-algae symbiont provided humanity with one of its most important chemical tools. Different organic molecules within the lichen extract change their structure, and thus the way they reflect light depending on the concentration of hydrogen ions around them. I'm curious, does anyone remember using litmus paper in a memorable or funny school experiment? Finally, in this world of donors and acceptors, there are the chemical chameleons. Some substances are classified as amphoteric, a term from Greek meaning in both ways. This means they have the remarkable ability to act as either an acid or a base, depending on their chemical environment. The most common and most critical amphoteric substance on Earth is water. If you mix water with a strong acid like HCl, the water molecules will act as a base, accepting protons to form the hydronium ion, H3O+. But if you mix water with a base like ammonia, the water molecules turn around and act as an acid, donating a proton to the ammonia. This dual personality is fundamental to the chemistry of water and is a key reason why it's such an incredible solvent and the foundation for life as we know it. Let me know what other examples of dual-natured things, chemical or otherwise, you find fascinating. It's this constant dance of giving and taking, of donating and accepting, that makes the world of acids and bases one of the most dynamic and essential fields in all of chemistry. Every single atom in your body, from the calcium in your bones to the iron in your blood, was forged in the heart of a dying star billions of years ago. You are, quite literally, made of stardust. Today, we're leaving Earth's laboratories behind and rocketing into the grandest lab of all, the cosmos, where the fundamental rules of chemistry paint the entire universe. We begin with the absolute basics. Just after the Big Bang, the universe was an incredibly simple place, chemically speaking. It was almost entirely composed of the two lightest elements, hydrogen and helium. In fact, even today, these two elements make up more than 98% of all the ordinary matter in the cosmos. Every other element on the periodic table is, in the grand scheme of things, just a trace impurity. All the complexity we see, from planets to people, is built from that remaining tiny 2%. But where did that 2% come from? The answer lies in the stars themselves, which are nothing less than colossal nuclear fusion reactors. The immense pressure and temperature at the core of a star fuses hydrogen atoms together to create helium. This is the simplest act of stellar chemistry, and it's what powers stars like our Sun for billions of years. But for heavier elements, you need a bigger star and a more dramatic process. As massive stars age, they begin fusing helium into carbon, then carbon into neon, oxygen, silicon, and so on, creating progressively heavier elements in layers, like a cosmic onion. This process, called stellar nucleosynthesis, is the universe's only element factory. Without it, the periodic table would stop at helium. Of course, forging those precious heavy elements inside a star is one thing. Getting them out into the universe is another. A star is a gravitational fortress. The elements created in its core are trapped there until the star dies. For the most massive stars, this death is the most spectacular chemical event in the universe, a supernova. When a giant star exhausts its nuclear fuel, it collapses under its own gravity and then rebounds in a cataclysmic explosion. This blast is so powerful, it not only scatters all those newly forged elements across interstellar space, but the sheer energy of the explosion itself actually creates even heavier elements like gold, platinum, and uranium. Every wedding ring, every piece of silver, is the ghost of an exploded star. From these stellar ashes, new wonders arise. The elements ejected by supernovae mix with interstellar gas and dust, forming vast, beautiful clouds called nebula. These aren't just empty wisps of gas, they are incredibly complex chemical environments. Astronomers using radio telescopes have discovered that these clouds are brimming with over 200 different kinds of molecules, and some of them are shockingly familiar. For instance, the giant molecular cloud Sagittarius B2, located near the center of our Milky Way galaxy, contains billions of liters of ethanol, the same type of alcohol found in beer and wine. It also contains vast quantities of a molecule called ethyl formate. This is the chemical compound that gives raspberries their distinct flavor and rum its characteristic smell. So, deep in space, there's a giant cloud that tastes of raspberries and smells of rum. Let's zoom in from these galaxy-spanning clouds to our own solar system, where the chemistry gets even stranger. On the ice giants, Uranus and Neptune, it literally rains diamonds. The atmospheres of these planets are rich in methane. The immense pressure deep within these planets, millions of times that of Earth's atmosphere, and intense heat can squeeze the carbon atoms out of the methane molecules, compressing them into solid diamonds. These diamond hailstones then slowly sink through the planet's slushy mantles toward the core. Imagine an entire planet with a layer of glittering diamonds thousands of kilometers thick. But it's not just exotic jewels. Chemistry is also responsible for one of the most fundamental questions astronauts are asked. What does space smell like? While the vacuum of space itself has no smell, the things floating in it do. Astronauts returning from spacewalks report a very distinct odor on their suits, which they've described as seared steak, hot metal, or welding fumes. Scientists believe this smell is caused by polycyclic aromatic hydrocarbons, or PAH. These are carbon-based molecules that are released from dying stars and are found clinging to space dust, comets, and asteroids throughout the universe. They're the byproducts of cosmic combustion, the lingering scent of stars being born and dying. If you had to describe the fragrance of the Milky Way, it would be a cosmic barbecue. What's the most surprising place you've heard of complex chemistry taking place? Drop your answer in the comments below. I'm curious to see the cosmic locations you can think of. Now, while we talk about exotic smells and diamond rain, let's not forget the most important molecule for life as we know it, water. We think of it as uniquely Earth's, but H2O is actually one of the most common molecules in the universe after molecular hydrogen. It's been detected in the atmospheres of gas giants, frozen on the surface of moons like Europa and Enceladus, and even found in the swirling disks of gas and dust that are forming new solar systems. In fact, astronomers have discovered a colossal cloud of water vapor floating in space around a distant quasar that contains at least 140 trillion times the amount of water in all of Earth's oceans combined. This proves the chemical ingredients for life aren't rare, they're everywhere. The chemistry of the cosmos even dictates what we see. The beautiful colors of nebulae and galaxies aren't random. They are chemical fingerprints. The brilliant red hues often come from glowing hydrogen atoms, while greens and blues can signify the presence of oxygen and helium. Even the color of a star tells its chemical story. Hot, massive young stars burn through their fuel rapidly and shine a brilliant blue-white. Cooler, older, or less massive stars, like our Sun, appear yellow, and as stars reach the end of their lives and cool down, they swell into red giants. The color is a direct indicator of its surface temperature, which in turn is a result of the nuclear chemical reactions happening deep inside its core. The entire night sky is a spectacular display of chemistry in action, a periodic table painted across a canvas of space-time, reminding us that from the simplest atom to the most distant galaxy, it's all connected by the same fundamental laws of chemistry. We've seen how chemists can link atoms to create the vast world of plastics and polymers, but what happens when we go further? When we stop just making materials and start engineering them, atom by painstaking atom, with a specific purpose in mind? Welcome to the architectural firm of the future, where the building blocks are individual molecules. Imagine taking a pencil, drawing a line and realizing that line is made of a material just one single atom thick. That's not science fiction, that's graphene. It's a sheet of carbon atoms arranged in a honeycomb lattice, and it's a material of superlatives. Graphene is about 200 times stronger than steel by weight, yet it's so thin and light that a single gram of it could be stretched to cover an entire football field. It's also one of the best conductors of electricity and heat ever discovered, and it's almost completely transparent. Discovered by simply peeling layers off graphite with sticky tape, this wonder material is poised to revolutionize everything from flexible electronics and super strong composites to ultra-efficient batteries. The sheer potential locked inside a single atomic layer of carbon is a testament to how arranging atoms in just the right way can completely change the rules of what's possible. From a flat, static sheet of atoms, let's get things moving. Chemists aren't just building structures anymore. They're building machines. Machines so small they are literally single molecules. The 2016 Nobel Prize in Chemistry was awarded for the design of these molecular machines. We're talking about molecules with moving parts that can be controlled to perform a task. A nanocar with a chassis and 4 wheels made from molecular groups that actually rolls across a surface when prompted by light or heat. Or a molecular elevator that can lift itself up and down a tiny axle. Or even a molecular motor that spins in one direction, powered by chemical energy, just like the motors in our own cells. This isn't just a party trick. It's the dawn of an era where we can deliver drugs to a single cell with a molecular truck, or build new materials from the bottom up with molecular robots. It's engineering on a scale that was unimaginable a few decades ago, manipulating matter at its most fundamental, movable level. If moving molecules around sounds incredible, what about controlling light itself just by changing a particle's size? That's the mind-bending reality of quantum dots. These are tiny crystals of semiconductor material only a few nanometers wide, so small they can be made of just a few thousand atoms. And here's where the magic of quantum mechanics kicks in. The color of light a quantum dot emits isn't determined by the material it's made of, but by its exact size. Make the dot a little bigger and it glows red. Shrink it down and it shifts through the spectrum to orange, yellow, and eventually blue for the smallest dots. This happens because shrinking the dot confines the electrons inside, changing their energy levels and thus the color of light they release. This precise, size-tunable color is why you see QLED on high-end televisions. They use a layer of these quantum dots to produce incredibly vibrant and accurate colors. They are tiny atomic light bulbs whose color is tuned by the simple act of addition or subtraction of a few atoms. Now, let's go from controlling light with tiny crystals to creating materials that are almost nothing but surface. Imagine a sugar cube. Now imagine that the internal surface area of that single sugar cube was bigger than a football stadium. That's the reality of a class of materials called metal organic frameworks, or MOFs. These are crystalline compounds made of metal ions linked together by organic molecules, forming a structure that is like a molecular scaffold. The result is a material that is incredibly porous on a nanoscopic level, creating the highest surface areas known to science. A single gram of some MOFs has a surface area of over 7,800 square meters. Their sponge-like nature makes them perfect for soaking up and storing gases. Scientists are designing MOFs to store hydrogen fuel for cars, to pull clean water from desert air, and, most promisingly, to selectively capture carbon dioxide straight out of industrial smokestacks. They are quite literally molecular cages, built atom by atom to trap specific molecules. What future material do you think will change our world the most? Let me know your thoughts down in the comments. From trapping molecules to actively repairing itself, chemistry continues to blur the line between the artificial and the biological. We've all seen a plastic object crack and known it was broken forever. But what if it wasn't? Chemists have developed self-healing polymers that can mend themselves when cut or fractured. Some of these materials are threaded with tiny capsules that rupture when the material is damaged, releasing a liquid healing agent that flows into the crack and hardens, like a chemical glue. An even more elegant approach involves building the polymer itself with reversible chemical bonds. When the material is torn, these dynamic bonds at the fractured surface can reform with each other, literally stitching the polymer chain back together with a bit of heat or light. We could one day have phone screens that fix their own cracks, car paint that repairs its own scratches, and medical implants that can mend damage while still inside the body, all by mimicking nature's own incredible ability to heal. But what if the goal isn't to be strong or self-healing, but to be almost nothing at all? Meet aerogel, the lightest solid material in the world. Often called frozen smoke or solid air, aerogel is a surreal, ghost-like substance that is made by taking the liquid component out of a gel and replacing it with gas without allowing the solid structure to collapse. The result is a material that can be up to 99.8% air. This incredible structure gives it astonishing properties. Despite being feather-light, it can support thousands of times its own weight. Its true superpower, though, is insulation. The tangled network of silica nanoparticles effectively traps air, preventing heat from passing through. An inch-thick pane of aerogel provides the same insulation as 30 panes of regular glass. It can protect a delicate flower from the direct heat of a blowtorch and has been used by NASA to insulate electronics on the Mars rovers from the planet's brutal temperature swings. It is the closest thing we have to solidified nothingness, engineered to be a perfect thermal barrier. From a material that holds air to a molecule that can hold all of human knowledge. Perhaps the most profound example of atomic engineering is using life's own blueprint, DNA, for data storage. Your computer stores data in binary, as ones and zeros, but a DNA molecule stores information using 4 chemical bases: adenine, A, cytosine, C, guanine, G, and thymine, T. Scientists have successfully translated digital data, books, images, and audio files into a sequence of these DNA bases. They then synthesize actual DNA strands encoding that sequence. The density is staggering. A single gram of DNA can theoretically hold around 215 petabytes of data. That's 215 million gigabytes. All of the information ever generated by humanity could be stored in a container of DNA about the size of a shoebox. Not only is it incredibly dense, but it's also unbelievably durable. While hard drives and flash memory degrade in decades, DNA can preserve information for tens of thousands of years. We are on the verge of storing our digital world not on silicon, but within the very same molecule that stores the code for life itself. Take a look at your hand. It seems solid, right? You can tap it on a desk, you can grab a cup. It's undeniably there. But what if I told you that on a fundamental level, your hand, the desk, the cup, and everything you've ever touched is actually 99.999% empty space? If you could somehow squeeze all the empty space out of every human on Earth, the entire species would fit inside a single sugar cube. That feeling of solidity you experience isn't matter touching matter. It's an illusion. It's the electromagnetic force fields of electrons repelling each other. You have never truly touched anything in your entire life. You've only felt the ghost of a force pushing back. This is the bizarre, counterintuitive world of chemistry at its smallest scale, where the rules of our world completely break down and the power of the tiny particle reigns supreme. This strange emptiness of atoms is just the beginning of the weirdness, because within that void, particles behave in ways that seem like pure science fiction. For instance, tiny particles like electrons don't have to obey the same rules as a baseball. If you throw a baseball at a wall, it will bounce back. But an electron, due to its quantum nature, has a certain probability of simply appearing on the other side of a barrier it shouldn't have enough energy to cross. This isn't breaking through the wall, it's more like teleporting. This phenomenon is called quantum tunneling, and it's not just a theoretical quirk. It's happening constantly, and it's the reason our sun shines. Think about the sun. It's a colossal nuclear furnace, smashing hydrogen atoms together to create helium and release immense energy. But here's the problem. Based on classical physics, the sun's core isn't actually hot enough or dense enough for those hydrogen nuclei, which are positively charged and repel each other, to get close enough to fuse. They should just bounce off each other forever. The only reason fusion happens at all is because of quantum tunneling. The particles tunnel through their own repulsion barrier, getting close enough to allow the strong nuclear force to take over and fuse them together. Without this tiny, ghostly leap through an impossible wall, our sun would be a cold, dark ball of gas, and life on Earth would have never begun. The power of a star is born from a particle's ability to cheat. If you could harness one quantum effect for a superpower, what would it be? Let me know your creative ideas in the comments. The weirdness of these particles goes even deeper. Take the electron again. It has a property called spin, which is one of the most misunderstood concepts in all of science. When you hear spin, you might picture a tiny ball spinning on its axis like a planet. But that's not what's happening. It's an intrinsic, built-in property of the electron, like its charge or mass. It just has spin. This spin can be in one of two states, which scientists call spin up and spin down. It's a purely quantum mechanical property with no real-world equivalent, but it's one of the most important properties in the universe. It's what makes magnetism possible, and even more critically, it's the key to why matter itself can even exist in the form we know. That brings us to a fundamental rule of the universe that's dictated by this mysterious spin, the Pauli exclusion principle. This principle, formulated by the brilliant chemist Wolfgang Pauli, states that no two electrons in the same atom can have the exact same quantum state. Since one part of that state is its spin, it means if you have two electrons in the same orbital, one must be spin up and the other must be spin down. The orbital is full. No more electrons allowed. This simple rule is the ultimate reason chemistry works the way it does. It dictates how electrons arrange themselves into shells around a nucleus, which in turn determines an element's chemical properties and how it bonds with others. More profoundly, it's the reason solid matter is solid. The electrons in your hand can't occupy the same space as the electrons in the desk because of this principle. They are excluded from each other's quantum territory. So while you're mostly empty space, the Pauli exclusion principle is the cosmic bouncer that prevents your empty space from just passing right through the desk's empty space. But electrons, protons, and neutrons aren't the only tiny particles that matter. The universe is teeming with other, even more elusive ones. Right now, as you sit there, trillions upon trillions of nearly massless particles called neutrinos are streaming from the sun and passing through your body every single second. They are passing through the chair you're sitting on and through the entire planet Earth as if it weren't even there. They are so weakly interacting that a neutrino could travel through a light year of solid lead with only a 50% chance of being stopped. They are the ultimate ghost particles. Silent messengers from the hearts of stars and cosmic explosions, carrying information across the universe completely unimpeded. We are all swimming in an invisible ocean of neutrinos, and we don't feel a thing. And for the grand finale of the tiny particle world, we have to talk about the most exotic and powerful substance theoretically possible: antimatter. For every particle of matter we know, like an electron or a proton, there exists an antiparticle with the same mass but the opposite charge. A positron is an anti-electron with a positive charge. An antiproton is its negative counterpart. These aren't just theoretical ideas. We create them in particle accelerators all the time. But here is where the power comes in. When a particle of matter meets its antimatter twin, they don't just collide, they annihilate each other completely, converting their entire mass into pure energy according to Einstein's E equals mc squared. The energy release is staggering. The annihilation of just 1 gram of antimatter with 1 gram of matter would release more energy than the largest nuclear bomb ever detonated. It is the most efficient and powerful energy source conceivable, but it's also incredibly difficult to produce and store. Its existence also poses one of the biggest mysteries in physics. If matter and antimatter were created in equal amounts in the Big Bang, why is our universe made almost entirely of matter? Where did all the antimatter go? The answer to that question could rewrite our entire understanding of the cosmos, all hinging on the behavior of these tiny, fundamental particles. And that very same atomic principle is why a diamond is forever. But the universe's most ingenious chemical engineering isn't found in a star or a stone. It's alive. In fact, it's probably crawling on your wall right now, defying gravity with a secret that took us centuries to crack. We're about to decode nature's chemical blueprint, where life itself is the ultimate chemist, and the reactions are nothing short of miraculous. Have you ever wondered about the magic of a firefly's glow on a summer night? It's not magic at all, but one of the most efficient chemical reactions known to science. Inside the firefly, a molecule called luciferin reacts with oxygen, catalyzed by an enzyme fittingly named luciferase. This reaction releases energy, but unlike a light bulb that wastes most of its energy as heat, this process is almost perfectly efficient. Nearly 100% of the energy from the chemical reaction is converted directly into light, producing what's known as cold light. It's a form of chemoluminescence so effective that scientists have harnessed it, using the luciferin-luciferase system in biomedical research to tag cells and track biological processes in real time. So every flicker of a firefly is a tiny, living beacon of near-perfect chemical engineering. From creating light to capturing it, nature's chemistry is the engine of our entire planet. You might think of photosynthesis as just plants using sunlight, but the chemistry is breathtakingly complex. At its heart is a process called photolysis, where the energy from a single photon of light is used to split a water molecule. This reaction, occurring billions of times a second across the globe, rips water apart into oxygen, protons, and electrons. That oxygen is what you're breathing right now. In fact, nearly all the oxygen in our atmosphere is a byproduct of this one specific chemical reaction. It's the most crucial photochemical process on Earth, turning sunlight, water, and carbon dioxide into the energy that fuels almost every food chain. And while photosynthesis builds life, another molecule stores the instructions. We talk about DNA as the blueprint of life, but chemically, it's more like the universe's most advanced hard drive. The information density is just staggering. A single gram of DNA can theoretically store around 215 petabytes of data. To put that in perspective, that's over 200,000 1 terabyte hard drives, all in a pinch of biological material. This incredible storage is achieved with just 4 chemical bases: adenine, guanine, cytosine, and thymine, arranged in a specific sequence. The 2 strands of the double helix are held together by hydrogen bonds, which are a chemical masterstroke. They're strong enough to keep the code intact, yet weak enough to be unzipped by enzymes for replication and reading the genetic instructions. It's a perfect balance of stability and accessibility, designed by billions of years of evolution. Nature's chemistry isn't just happening in forests and cells, it's happening right in your kitchen every single time you cook. That delicious, savory crust on a seared steak, the golden brown color of toast, the rich aroma of roasting coffee, you can thank a process called the Maillard reaction. It's not a single reaction, but a cascade of complex chemical changes that occur when amino acids from proteins react with sugars under heat. This chain reaction creates hundreds of new, complex molecules, each with its own unique flavor and aroma. It's the reason why boiled meat tastes so bland compared to grilled meat. It's the art of browning, and it's responsible for some of the most craved flavors in the world. What's the one food you can't live without thanks to the Maillard reaction? Let me know your delicious answer in the comments. But chemistry doesn't just create flavor, it can create powerful illusions. Think about the burning sensation from a chili pepper. That's not a taste like sweet or sour. It's a brilliant chemical deception. The molecule responsible, capsaicin, fits perfectly into a specific receptor on your nerve cells called TRPV1. The normal job of this receptor is to detect actual physical heat, to warn you if you're about to burn your tongue on hot soup. But capsaicin is a molecular imposter. It binds to that receptor and triggers it, fooling your nervous system into sending the exact same pain and heat signals to your brain as a real burn. That's why your brain screams fire and you start sweating, even though your mouth is at a normal temperature. It's a complete sensory hallucination engineered by a single molecule. From imitation to outright chemical warfare, nature's chemical arsenal is terrifyingly potent. A snake's venom, for instance, isn't a simple poison. It's a highly sophisticated cocktail of dozens, sometimes over 100, different proteins and enzymes, each with a specific, deadly mission. The venom of a rattlesnake, for example, is loaded with hemotoxins, which are designed to obliterate blood. They destroy red blood cells, prevent blood from clotting, and cause catastrophic internal bleeding. In contrast, a cobra's venom is packed with neurotoxins that wage war on the nervous system. They block nerve signals from reaching muscles, leading to paralysis and, ultimately, shutting down the victim's ability to breathe. Each drop is a weaponized library of evolutionary chemistry. But what about that gecko we mentioned, casually strolling across your ceiling? How does it defy gravity with such ease? For years, scientists speculated about suction cups or a microscopic glue. The truth is far more elegant and rooted in fundamental physics. A gecko's feet are covered in millions of tiny hair-like structures called seta. But it gets even crazier. Each of those seta splits into hundreds of even smaller, nano-sized tips called spatulae. This creates an unimaginably vast surface area. When the gecko puts its foot down, the electrons in the molecules of its spatulae and the electrons in the molecules of the wall surface interact. This interaction creates a subtle electromagnetic attraction known as the van der Waals force. A single one of these forces is incredibly weak, almost non-existent. But with billions upon billions of contact points, these tiny forces add up to create a powerful adhesive bond, strong enough to let the gecko hang its entire body weight from a single toe on slick glass. It's not a biological trick, it's the raw power of intermolecular chemistry in action, allowing life to literally. Imagine a liquid so corrosive it will eat through the glass container you're holding, your lab bench, and the floor beneath it. This isn't science fiction. This is the world of extreme chemistry, where the fundamental rules get pushed to their absolute breaking point. We've explored the elements, the reactions, and the molecules that build our reality. Now, we're venturing into the abyss, where chemistry gets wild. We start with that glass-dissolving liquid. It's called fluoroantimonic acid, and it holds the undisputed title of the world's strongest superacid. To give you some perspective, the pH scale we all learned in school basically becomes meaningless here. This acid is an astonishing 10 quadrillion times stronger than 100% pure sulfuric acid. It's so powerful because it's a master at giving away protons, the very definition of an acid. Its eagerness to do so means it will forcibly protonate and then violently decompose nearly any organic compound it touches. Hydrocarbons in plastics or human flesh are instantly torn apart. It reacts explosively with water and can only be stored in special containers lined with Teflon, one of the very few things it can't easily destroy. And just as nature loves balance, for every impossibly strong acid, there's an impossibly strong base. While superacids are desperate to give away protons, superbases are desperate to rip them away from other molecules. The reigning champion is a mind-bending molecule called orthodiethylbenzene dianion. Synthesized in a laboratory, it is the strongest base ever created. It can deprotonate almost anything, even famously stable molecules like benzene, a feat previously thought to be chemically near impossible. Its extreme reactivity makes it incredibly difficult to work with, a fleeting chemical ghost that exists only under the most controlled conditions before it tears a proton from whatever is nearby. From extreme reactivity, let's plunge into extreme cold. You've probably heard of absolute zero, but what it represents is truly profound. It's zero on the Kelvin scale, or minus 273.15 degrees Celsius. This is the theoretical point where all classical thermal motion of atoms ceases. They stop vibrating, stop rotating, stop moving. It's the ultimate stillness. However, there's a fascinating quantum twist. Even at absolute zero, atoms don't become perfectly stationary. They still possess a tiny residual shudder of energy known as zero-point energy, a fundamental consequence of the Heisenberg uncertainty principle. You can know where the particle is, but you can't know its momentum is exactly zero at the same time. So even at the coldest temperature in the universe, there's a quantum ghost in the machine. Getting to absolute zero is impossible, but what happens when we get incredibly close, within a few billionths of a degree? We unlock a completely new state of matter. At these ultra-cold temperatures, quantum effects take over on a massive scale. Atoms slow down so much that their wave-like nature starts to overlap. Eventually, they snap into the same quantum state, losing their individual identities and beginning to behave as a single massive superatom. This is a Bose-Einstein condensate, the fifth state of matter. It's a cloud of atoms acting in perfect, eerie unison, a macroscopic glimpse into the strange rules of the quantum world. So we've been to the coldest possible place, but what about the hottest? How hot can chemistry get before matter itself just gives up? Scientists have a theoretical limit called the Hagedorn temperature. Clocking in at around 2 trillion degrees Celsius, this is the point where hadronic matter, the protons and neutrons that make up atomic nuclei, can no longer exist. The energy is so immense that the quarks and gluons that form these particles are liberated, melting into a primordial soup known as a quark-gluon plasma. This is the state of the entire universe for the first few microseconds after the Big Bang. It's not just hot, it's a temperature that fundamentally dissolves the building blocks of you, me, and everything we can see. If you could somehow travel back to that moment, what do you think that soup would even look like? Let me know your most creative description in the comments below. Temperature isn't the only dial we can crank up to 11. Pushing pressure to the extreme also creates bizarre forms of matter. Take hydrogen, the simplest element. Under normal conditions, it's a transparent gas. But if you squeeze it with the pressure of millions of Earth atmospheres, the kind of pressure found deep within the core of Jupiter, something incredible happens. The hydrogen atoms are forced so close together that their electrons are no longer bound to a single nucleus. They become delocalized, forming a sea of electrons that can flow freely. The hydrogen transforms into an electrical conductor, a shiny liquid metal. This metallic hydrogen is one of the holy grails of physics and chemistry, not just because it explains the interiors of gas giants, but because it's predicted to be a room-temperature superconductor, a material that could revolutionize energy and technology forever if we could ever create and stabilize it. Now, let's dial reactivity back to the max, with a compound so dangerous it makes nitroglycerin look like a children's toy. Meet azeto-azide-azide, with the chemical formula C2N14. It is one of the most explosive chemical compounds ever created. It belongs to a class of materials called high-nitrogen energetic materials, and its structure is a chemist's nightmare. It's made of 2 carbon atoms holding this incredibly unstable arrangement of 14 nitrogen atoms, all straining to break apart. That strain holds an immense amount of energy. The bonds are so fragile that almost anything can set it off. A slight touch, a bright light, a change in temperature, or even, in some tests, simply leaving it undisturbed on a spectrometer. Scientists who have studied it do so in minuscule quantities behind multiple blast shields because its decomposition into nitrogen gas is almost instantaneous and breathtakingly violent. We'll end this journey to the edge with a discovery that rewrote the textbooks. For decades, the noble gases, helium, neon, argon, xenon, were considered the VIP section of the periodic table, completely aloof, inert, and too noble to react with anything. Their full outer shells of electrons made them perfectly stable and, it was thought, chemically unassailable. This was a fundamental rule of chemistry until 1962. A chemist named Neil Bartlett noticed that a powerful oxidizing agent could steal an electron from an oxygen molecule. He realized that the energy required to do this was very similar to the energy needed to steal an electron from a xenon atom. In a daring experiment, he mixed xenon gas with this agent, platinum hexafluoride, and it worked. He created xenon hexafluoroplatinate, a stable orange-yellow solid. It was the first ever compound made from a noble gas, shattering a century-old chemical dogma. It proved that under the right extreme conditions, even the most unshakable rules are made to be broken. Look at your hand. Now, think about the stars. What if I told you the atoms that make up your fingernails were forged in the heart of a dying star billions of years ago? That's not poetry, that's chemistry. In this final part of our journey, we're putting on a new pair of glasses to see the hidden chemical world that shapes our entire reality. If you've loved discovering the secrets of the elements with us, make sure you're subscribed so you don't miss what's next. Now, let's begin. We spend our entire lives breathing, but we rarely think about what we're actually breathing in. It's mostly nitrogen, but the crucial part is oxygen, O2. 2 oxygen atoms bonded together. But this element is a chemical chameleon. Add 1 more oxygen atom and you get O3, also known as ozone. This molecule forms a fragile layer in our stratosphere that acts like planetary sunscreen, absorbing the sun's most harmful ultraviolet radiation. Without that specific 3-atom arrangement, life on land as we know it would be impossible. and it's ozone, along with other atmospheric molecules, that scatters sunlight in a way that paints our sky blue. But oxygen isn't done. If you cool it down to -183 degrees Celsius, it becomes a beautiful pale blue liquid. Cool it even further to -218 degrees Celsius, and it freezes into a pale blue solid, forming delicate crystalline structures. The same element that fuels our bodies and paints our skies can exist as a solid, a liquid, and a gas, all with fundamentally different properties. But oxygen's artistic talents aren't limited to the sky. It's also a master jeweler. Consider the mineral corundum. In its purest form, it's just aluminum oxide, 2 parts aluminum, 3 parts oxygen. Chemically, it's quite simple, and on its own, it's completely colorless and not particularly exciting. But this is where the magic of chemistry truly shines. Introduce a tiny, almost insignificant impurity. Replace just a few aluminum atoms in the crystal lattice with chromium atoms, and suddenly that dull, clear crystal begins to absorb green and yellow light, letting only deep red light pass through. You've just created a ruby, one of the most precious gemstones on Earth. Now, what if the impurity isn't chromium? What if it's a few stray atoms of iron and titanium? Those tiny chemical imperfections cause the crystal to absorb different wavelengths of light, resulting in a deep, brilliant blue. You've just made a sapphire. 2 of history's most coveted gems are chemically almost identical, separated only by a few rogue atoms that we would normally call an impurity. From nature's imperfections to human ingenuity's pursuit of perfection. For centuries, we thought materials had to be 3-dimensional. But then, we isolated a substance that breaks all the rules: graphene. It's made of pure carbon, the same element that makes up diamonds and pencil lead. But in graphene, the carbon atoms are arranged in a flat, 2-dimensional honeycomb lattice that is only one single atom thick. Imagine a sheet of material so thin that a stack of 3 million layers would only be 1 millimeter high. Despite being virtually transparent and unimaginably thin, graphene is the strongest material ever tested, about 200 times stronger than steel by weight. A hypothetical sheet of graphene, the thickness of kitchen plastic wrap, could support the weight of a full-grown elephant. It conducts electricity better than copper and heat better than any other known material. It's a true wonder material that is rewriting our understanding of what's possible. The potential applications for materials like this are staggering, from flexible electronics to super strong composites. What's the most futuristic use of a material like graphene you can imagine? Drop your sci-fi ideas in the comments below. Carbon doesn't just build the future, it tells us stories about the past. In our atmosphere, there's a stable, common form of carbon called carbon-12. But there's also a tiny, predictable amount of a heavier, radioactive version called carbon-14. This carbon-14 is created when cosmic rays strike nitrogen atoms high in the atmosphere. Every living thing, from the tallest tree to you and me, is constantly absorbing this carbon from the environment. As long as an organism is alive, the ratio of carbon-12 to carbon-14 in its body matches the ratio in the atmosphere. The moment it dies, however, that intake stops. The carbon-14, being unstable, immediately begins to decay back into nitrogen at a perfectly constant rate. Its half-life is 5,730 years, meaning that after this time, exactly half of the carbon-14 atoms will be gone. By measuring the amount of carbon-14 left in an ancient bone, a piece of wood, or a fragment of cloth, scientists can precisely calculate how long ago it died. It's chemistry's own time machine, allowing us to accurately date artifacts up to 50,000 years old. This kind of precise, predictable chemical clockwork is amazing. But some reactions are the complete opposite: chaotic, violent, and explosive. And one of the most brilliant examples of chemical warfare is wielded by a tiny insect, the bombardier beetle. This beetle has evolved a defense mechanism that is nothing short of an engineering marvel. Inside its abdomen, it has two separate chambers. One holds a solution of hydroquinones and hydrogen peroxide, harmless on their own. The other chamber is lined with enzymes that act as catalysts. When the beetle feels threatened, it squeezes the contents of the first chamber into the second. The moment the chemicals mix with the enzymes, a runaway chain reaction begins. The reaction is so violently exothermic that it heats the mixture to 100 degrees Celsius, the boiling point of water. This creates a massive buildup of pressure, which the beetle then releases through a steerable nozzle in its abdomen, firing a boiling hot, toxic chemical spray at its attacker with an audible pop. It can aim this spray with incredible accuracy, demonstrating a mastery of high-speed chemical reactions that would be the envy of any lab. This principle of mixing chemicals to create a powerful effect has been adopted by humans, sometimes with incredibly divergent results. Take nitroglycerin. The name alone conjures images of instability and danger. It's a key ingredient in dynamite, and for good reason. It's a notoriously volatile and powerful explosive. But here is the chemical twist that could save your life. That exact same molecule, when administered in a very small, controlled dose, is a powerful medicine. Nitroglycerin is a vasodilator used by heart patients to treat angina or chest pain. When it enters the bloodstream, the body's enzymes break it down, releasing nitric oxide. This tiny molecule signals the smooth muscles in the walls of blood vessels to relax and widen. This increases blood flow and oxygen supply to the heart muscle itself, relieving the pain and strain. It's a stunning duality. The very same chemical compound that possesses the raw power to shatter rock is also delicate enough to heal the human heart. And that brings us to the final, most astounding fact of all. It's the thread that ties everything together, from the oxygen in the sky, to the carbon in ancient bones, to the complex molecules in our own bodies. The final fact is you. You are not just a body that contains chemicals. Your entire existence is a chemical process. Every single thought firing in your brain is a cascade of neurotransmitters: serotonin, dopamine, acetylcholine, crossing a synaptic gap. Every heartbeat is driven by the precise movement of sodium and potassium ions across cell membranes. The color of your eyes is determined by the specific chemical structure of melanin pigments. The DNA that contains the blueprint for your entire being is a double helix polymer, a magnificent chemical code written in a language of 4 simple molecules. You are a self-sustaining, self-replicating symphony of trillions upon trillions of coordinated chemical reactions happening every single second.
You are the universe's way of understanding itself, a collection of stardust rearranged by the fundamental laws of chemistry into a conscious being capable of awe and wonder. And that is the true power of this science. Chemistry isn't just about beakers and lab coats. It's the instruction manual for reality itself.
It connects the birth of stars to the bloom of a flower, and the bloom of a flower to the thought you're having right now. It is a new lens. And once you learn how to see the world through it, nothing ever looks the same again. Thank you for taking this incredible journey with us. If you've enjoyed looking at the world through the eyes of a chemist, show your support by liking this video and subscribing for more adventures into the fabric of our universe. Until next time, stay curious.